Okay, so yesterday we studied that in a microcanonical ensemble, each state, the probability of finding any particle or a probability of finding my system in any micro state, P of mu is equal to 1 over omega some state of energy E comma x is 1 over omega. Okay, so let me start from the beginning. Okay, so we looked at the probability of finding a microstate with energy E and x goes as 1 over omega E comma x times 1 0. This is if the Hamiltonian is equal to E. This is otherwise. Okay, so I have these equations. So this is the fundamental relationship we'll use, or equation, right? And this we also call this as the central postulate. Okay, so now let's look at a system and this, and how do we solve the system. So the problem which I'm going to describe is I have a crystal, right? So I have a crystal and we all know the crystal will have defects. So I have a crystal. The crystal will have defects, and these defects can be either that some of the arrangement within the crystal is not right, or due to the presence of some impurities. So now the problem statement is I have a crystal and it has n impurities present in it. Okay, n is the number of impurities that is present in it. And remember, in in the values of n we are dealing with, all these are large numbers. Okay, it's not one or two impurities. These n is a very large number. Only then we can describe them by statistical mechanics. Okay, so these impurities, the problem statement is they can be present either in a ground state. So for example, let's say if these impurities are somehow able to sit here, right? And let's say some are maybe sitting in where even, let me see, it can be of different orientation. They are sitting in different orientation, different places within the crystal. So depending on where they sit, they can either be in this blue state, or let's say they are in green state. Okay, and remember, what is the thing we have? We have the number of blue and number of green is n. So I have n impurities present. That I can either be present in the blue or in green. And blue state, I mean, it's a ground state. Where the energy is 0, or in an excited state where my energy is epsilon. So I hope everybody is following this. So I have an impurity. It can either be present in a ground state or it can either be present in a excited state. Okay, so this is the problem statement. Now I need to use microcanonical ensemble to solve this. So the statement till now is actually, it's a macroscopic thermodynamic statement, kind of, right? You have some impurities. I can either be in a ground state or excited state. Now the question asked is calculate how the energy of the crystal varies with respect to temperature. Okay. So looks very daunting, right? But if you just follow the steps, the problem just solves itself, right? So what is the first step when you're if you're using tools of statistical mechanics? The first step is to first identify the ensemble. Okay, this is the first step. What does this mean? It means that, okay, I want to solve the problem. And so should I go and look for boxes which have constant n, v, and e, or should I go and look for boxes which have constant n, v, and t? Right? What boxes will you take? That is the first for your analysis. Depending on the box you take, the potentials you want to minimize changes and the relation will change, right? So now that we only know microcanonical ensemble, you are left, but you don't have any choice. You have to choose a microcanonical ensemble. So what do you do? So now you choose identical copies of these systems where the total number of particles is n, that is fixed, the impurities are fixed, so it's you consider it like a closed system. And of course it is a closed system, right? So there's no adsorption or anything taking place, so all the impurities are trapped in the crystal. And volume, instead of volume we can say, yeah, crystal volume is also constant, but we generally don't discuss volume for this system, right? Because there is no, it's a solid and variation in volume is not, is negligent. And E is the energy. So you don't know anything about E as of now. The only thing what you know is I have a system. It can be in ground state with the energy 0, or it can be in an excited state with the energy epsilon. This is for a single impurity. So now what you do is you say that, no, I'm going to make an ensemble with constant energy E and N. So it's like going and picking boxes with some energy only if those boxes have this energy E. Okay. Is everybody following? Yeah. So now I look at this system, and then I need to define the microstate. So you define the ensemble. I'm going to do the microcanonical ensemble. So then we say, what does that mean? It means I'm going to only pick these boxes. Then once you have decided I'm going to do this, you need to decide what is the microstate. What is the microstate? So here you don't have to worry about position, momentum, etc. Right? So for this problem, a microstate is something which completely defines in what state the system is in, right? So here you have n impurities. What is that equation which completely gives you what the state of the system is? So if I tell you that what each impurity in what state it is, that will give you the entire system, right? So if I tell n1 is in, so let me just put, if I put up arrow, that means it's in a or better than that, if I say 1, it is in a it is in a excited state. If I put 0, it is in a ground state. So there are n impurities. So if I have something, a string like this, right? So if I have this completely defines the microstate of the system. Okay, is everybody following? Yeah. So if I have such systems, so let's say if I have 1 1 1 0 0 0 0, so this again says that my third impurities are in excited state, the rest are in ground state, etc. So a microstate is defined by all this. Okay. So a microstate is defined by all of this. And for this system, I'll say Ni Ni is nothing but, how do I define Ni? Ni can either be 1 or 0, correct? So this is the microstate of a single impurity. Okay. Any questions with this? Okay. Now I need to calculate probability of Ni, but this is just for I goes from 1 to n. Remember, there are n impurities. Okay. So what would be the total Hamiltonian of the system? Hamiltonian associated with a state Ni, it is nothing but epsilon times sigma Ni. I goes from 1 to n, right? So if I have all the impurities present in the excited state, all the Ni's are 1. So it will become n epsilon. In other case, if all the impurities are present in ground state, all the Ni's are 0, your Hamiltonian is equal to 0. Okay. So how do I define the P of Ni? P of Ni is 1 over omega of E times 1 if Hamiltonian of Ni is equal to E. That means my epsilon times sigma I equals 1 to n is E, and it is 0 otherwise. Okay. I hope all of you are getting this. Okay. So now I need to solve this, right? So you have chosen the box such that it has the total energy is E. So now I'll assume that since my energy is fixed, now I need to change, right? I'll assume that let N1 be the number of impurities which are in the ground state. And I'll consider now, just because of the total number is fixed, n minus n1 are the number of impurities which are in excited state. I think just to make things easier, what I'll do is I'll make n1 as the number which is in excited state and n2 as the number which is in ground state. Nothing will change. It is just so that I can, the total energy is E. So N1 epsilon is E. I can write this, right? So only for that, I just made this. It doesn't matter what you consider. So you can consider N1 to be in ground state, then N minus N1 will be excited. So you can swap this. The answers, etc., won't change at all, right? So what is N1? N1 becomes E to E divided by epsilon. So N1 is the number of impurities which are in the excited state. So if I divide the total energy by epsilon, epsilon is if one atom is in the excited state, what is the energy? Then I'll get the total number N1. Okay. So remember, to kind of solve this problem, what do we need? We need epsilon E. Sorry, not epsilon E, omega of E. Okay. I need to calculate omega of E. And omega of E, what is omega of E? Omega of E contains is the number of states that have the same energy E. What does that again mean? It means the number of states which have the same energy E. So, right? So that means I can have these arrangements, right? So I'm just writing for maybe 6 systems, right? I have 0, 1, 0. 0, 0, 0, 1, 1, 1, so on and so forth. I can write many such. What is constant here is all these have the total energy is kind of 3 epsilon here, right? But if you look at this, these are all different arrangements of the same system. So the here N1 impurity is in the excited state, whereas here N1 is in the ground state. So these are different microstates. Remember, all these are different microstate. So what is omega e comma n? Omega e comma n tells me how many such states. So you count how many such states are there which have the energy E. And that energy E we defined. We said I'm only going to choose systems with some energy E. Okay. So that is what this means. And what is also very kind of evident here is we don't kind of care. We are only worried about the total energy E. So we don't care if how we arrange these in a when you look at the microstates, right? So we are taking all the microstates which have energy E. Here I have just for representation I have written 3 epsilon, but in case in general for the to solve the problem we are taking all the states which have the energy E. Okay. So this we know. How do I calculate omega E comma n? This is nothing but number of combinations or number of identical permutations of identical things. So you can think in both ways. Okay. So I have the total n impurities have. So I have n factorial. There is n minus n1 of type which are in the ground state, and there are n1 which are in the excited state. Okay, so this gives me the number of arrangements. This is same as the coin toss problem, okay, which we discussed in class. The question is how many ways I can get. Let's say I toss the coin 10 times. The question is just how many times how many such strings or the microstates are there where I get 5 heads, right? So I don't care when the head happens. If the first toss a head or second, no, I don't. I just take the sum and I want to calculate all those states where the sum is equal to 5 heads. Okay. Now I have omega is this, right? So first, this is the next step in calculating the microcanonical ensemble. I have omega. And now once I have omega, I know my entropy. S of E comma N is nothing but KB ln gamma omega. So I got KB ln n factorial divided by n minus n1 factorial times n1 factorial. Okay. So this ln n factorial, we'll use something called the Stirling's approximation. Okay. So, and what does it say for large n? Ln of n factorial can be approximated to n ln n minus n. Okay. So this is my Stirling's approximation. So once I'm not going to do the simplification here. So I let all of you try this, and if some of you have already done, that's even better. So this becomes S of E comma n is minus n kb, and I have substituted in place of n1, I have substituted E by epsilon, remember. So this becomes E by n epsilon ln E by n epsilon plus 1 minus E by n epsilon ln 1 minus E by n epsilon. Okay, so this is the equation. Now this just gives the entropy as the function of energy and the number of impurities, right? So I want to calculate, let's say, how my energy as a function of temperature, for example, right? So remember, till here we used the statistical mechanics, and then we came back S of E comma N, we came back to my macroscopic thermodynamics using the Boltzmann formula. S is k log omega, so we used that and we came back to macroscopic thermodynamics. Once I'm in macroscopic thermodynamics, I want to calculate now how uh, energy varies as temperature. What do I use here? I'll use, I know 1 by T is, this is the consequence of first law. I can say at constant x here in, if I keep constant. So I know this relation. So just substituting that, if I differentiate this equation S E comma N, so this just with respect to E, I'll get minus KB by epsilon ln E by N epsilon minus. Okay. So I'll get this equation. So just by simplification, I can also get how uh, I can write E as a function of T. Okay, so this is the final equation. I get E of T, the energy as a function of T. So what is evident here is, you look at this system. So this is again a binary system, right? It's a two-state system. So sort not binary, I would say it's a binomial distribution, because there are only two binary outcomes, right? It can either be in ground state, energy 0, or excited state times. So these are the energies possible, right? Either it's 0 or epsilon. Now, if I ask you a question that you have a coin toss and you have it's a fair coin, let's say, let's assume it's a fair coin, okay, and you toss the coin 10 times or 100 times. If I ask you after so many trials, what would be the number of heads and tails? So you will say that equal number of heads and equal number of course it won't be equal, right? So there will be fluctuations, and these fluctuations will go down as the number of trials, as n tends to infinity, as your number of trials go. Okay, but you would, it's a general kind of guess that since it's a fair coin, you'll have half of heads and half of them are tails. And even here, there are two cases, right? Either it can be ground state, excited state. At very high temperature, as T approaches infinity, what happens to this system? So this denominator e to the power epsilon by kt will become 1, because e to the power, it will become e to the power 0 plus 1. So I'll get E of t is n epsilon by 2. So what does that is telling you is that as t tends to infinity, what is the driving force? Remember, entropy is the driving force. And when entropy is the driving force, the system will tend to maximize omega E comma n. And what arrangement of zeros and ones will maximize omega? So it's an arrangement where there is equal number of zeros and equal number of ones. So that means half of them are in the ground state, half of them are in excited state. And we know what is the energy of those such states. So I'll have n by 2, which are in ground state. I'll just take n by 2, which are in excited state. So final answer is n epsilon by 2. So that is what we are getting. Okay. Now in the limit as t tends to 0. So I have E of t is given as n epsilon e to the power epsilon by kt plus 1. So in the limit as t tends to 0, what happens? Remember, as t tends to 0, entropy actually tends to be 0. So this is not kind of a entropy does not control the equilibrium of the system. It's mostly determined by the energy, and they want to be in the lowest energy at that time, right? At t tends to 0. So if I look at substitute t equals 0, denominator becomes infinity, so E of t becomes 0. So this is telling you that if my system at very low temperatures, most of these impurities will be present in the, all of the impurities will be present in the ground state. At very high temperatures, half of the impurities will be present in the ground state. Okay. So this is counterintuitive, right? Which is, so the 0 thing is not counterintuitive. I know that at lower temperature energy will take the state which lowers the energy, so that is not counterintuitive. But the fact that generally all the functions we have studied such that, what is it, we have dou s by, we just did this, is 1 over t. So as E increases, S will increase, correct? Because t is always positive. As E increases, S will increase. But here, for this two state system, that is not true, right? As I'm increasing t, E will increase only up to, so if I plot a graph, you'll see that if this is my t and this is my energy, so it is 0 here. So plot t. Now we know that in the limit at t tends to 0, it is 0, then it approaches n epsilon by 2. So, but what about this region? So generally, what is it? If I increase energy, the entropy will increase, correct? That's how we have studied for all systems. But for this systems, if my energy, let's assume E is, let's take the extreme case, everything is in the, everything is in excited state. So then what will be my energy? My total energy E will be n epsilon. That means every state is just 1, 1, 1, 1. And we know this has the least entropy. So at high temperature, we will expect that energy will be very high. But here and also entropy is very high. But for this two-state system, what is happening is that increasing energy beyond this n epsilon by 2 is actually decreasing the entropy. Remember, this is not true for most of the systems we'll study. For it's only applicable for some of the systems uh, which are in metastable equilibrium, and it happens especially you take into quantum effects into picture. Only those systems exhibit this, but it's also a very good exercise to think about what is happening here, right? So, and if let's say I start my system somewhere here. Okay. Generally, what happens to my system if I add heat to the system? Let's look at two scenarios. If I add heat to the system, generally speaking, the temperature will increase. And if I remove heat, the temperature will decrease. Correct? So this is actually true for this portion. So I'll just write this positive temperature. Okay. So for this system, if you look at this, as I'm increasing T, energy is increasing. That means if I'm adding heat to the system, so this is, if I'm adding heat to the system, temperature is also increasing. Whereas if I'm removing heat, the temperature is also decreasing. Whereas for this system, we'll say this region, or this region, we'll call this negative temperature. This does not mean that temperature is going below 0 Kelvin. It does not mean negative temperature in that aspect. What does this mean is that if I add heat, temperature actually goes down, and if I remove heat, temperature actually goes up. It's extremely counterintuitive to think, right? So we generally know if I add heat to the system, temperature will increase. If I remove heat, temperature will decrease, right? Assuming I'm not doing any work, etc. Just looking at the transfer of heat. But this is extremely counterintuitive. Why this is happening is because of this. Generally for systems, as I increase the energy, the entropy will increase. But for this system, beyond this energy of n epsilon by 2, if I increase the energy, entropy is decreasing. Look at this. As a result, if I add heat, let's say if I'm a system here, if I'm adding heat, what will happen to this? I'm adding heat to it, so energy will increase or decrease. Energy has to, I'm adding heat, energy will increase. Energy increasing means my temperature will go down. So remember, it's only applicable for this negative temperature system. And if I remove heat from this, the temperature will increase. Okay. So this is a very special case and only applicable for this two-level systems. And then we can actually calculate some of the properties, right? Once I have E of T, the specific heat I can calculate dE by dt. So this goes as n epsilon kb. So this looks like a big equation, but it is just obtained by solving. So I know E of T, right? So I think yeah, I have E of T here. E of T is n epsilon by, so I have E of T. I just have to differentiate this with respect to T. That's it. And I'll arrive at this equation. Okay. And how does this curve look? And I know that at very low temperatures, as a consequence of third law, if you remember, as T approaches 0, all the specific capacities go to 0. That is what happens here also. You can substitute in the limit T approaches 0. So I have this square term here. So this goes to 0. And as T approaches infinity also, it goes to 0. You can check that. Okay, right? So at T approaches infinity, also this goes to 0. So this curve would look something like this. It'll have a maximum somewhere. So I'll say here I'm plotting C by NKB, and here I have epsilon by KB. Okay, so this is the specific heat of the system. Okay. Now I can even draw the probability of finding my state in each of these. So if I just plot, this is the probability of finding my system in some micro state, right? So if I say this is my, this is P of N1 is 1, that means my system is in excited state. How will the ground state probabilities look? So it will be just, I know the sum should be 1, so this is half. This is how this will look. Let me just redraw this. So this will look something like this. They just complement. Okay. So this is all we have for the two-state system. Now I'll be happy to take any questions we can discuss about this. Okay.